Everybody's here today, but maybe I'll video to it in case you want to see it again. If you look at the schedule we had, the other class, the honors class, and this is where we start diverging a little bit, is they have their test today. And your test is very similar to theirs, except I'm going at a slower pace. And you guys don't even have your test till Friday, do you? So I'm hoping that we'll have time to wrap things up. This is an unusual week because you have the PSAT on Wednesdays, don't you? But you actually have this class. It's just that you have PSAT in the morning. So we're going to try to wrap up things today and Wednesday. And I have an entire day, Thursday, where I have a practice test. It's actually 2 different practice tests made by 2 different students in the past. And I would like that day to be where I just walk around the room, and if you're having trouble with one, then I just help you like that. So it's still your responsibility to learn this material. I'm going to try to teach it the very, very best I can. It's your responsibility to say, now I know how to do this. And so we'll have, the way it is now, we should wrap the chapter up, almost finished today. We'll probably finish on Wednesday. And then all day Thursday, all you do is a practice test. And you can look things up and say, oh yeah, that's right, I got to go back and look at my metric prefixes. Oh yeah, I got scientific notation, see that? So that's where we're at right now. And so I don't know if you remember where we left off. I think, have we done the temperature scale? Did I do a little dumb little song for you and everything? Remember that? Okay. All right, let's go to that page there. And if you have a calculator, go ahead and get that out. If anybody needs to borrow a calculator, if anybody need to borrow one? All right, I got him first, but you guys might be able to have to share a calculator because I only have one. Here you go. And just kind of, you do one, she could do one like that. All right, here we go. So we're going to try to get a lot of things done today. I'm not on the camera yet, but the temperature scales, there are 3 of them I'd like you to know. The rest of the world doesn't care about Fahrenheit. And unless you become an engineer or a chemist or a biologist, probably chemist, you probably won't worry about Kelvin either. The Kelvin scale, and we'll talk about that again today, it is the one that they use in the metric system, the SI system, and we'll talk about why in just a minute. But I would say that for sure you should know a little bit about Fahrenheit because you live in the United States. So look up here again. I can't think of any reason why somebody in the United States wouldn't know the freezing temperature, the freezing point of water. Without looking, do you know the freezing point of water in Fahrenheit? It's kind of unusual, right? But what is that number? It's a weird number. What is it? 32. So 32 degrees Fahrenheit is where ice forms, isn't it? Now, if you had water and you froze it, it'd be called the freezing point of water. What if I had ice and I started to melt it? It'd be called the melting point of water. That's the same temperature, isn't it? If it's already ice and you heat it, you get up to 32, it starts melting, doesn't it? If it's liquid water and you start freezing it, it starts solidifying at 32. It's the same temperature. Very few people in the United States know the temperature that water boils at in Fahrenheit is 212. Again, we got these weird numbers, don't we? How about 98.6? Is that pretty much, body temperature soar around there? Something close to that? Okay. And a comfortable room, I would say most people would say 72 is a pretty comfortable room. All right, so that's what you know in Fahrenheit, right? Let's go to Celsius scale. And remember, this came along with the metric system, and they wanted everything to be easy to remember. And they knew water was really big. Water's a big thing for humans. You understand that? You die without water. You can actually live probably a month without food. You wouldn't feel good, but you could probably go a whole month without food. But you aren't going to go more than a week. Maybe, I don't think you can make it a week without water. Water is essential. It's kind of neat how God gave us a planet that is covered with water. And we have water in the air, water in the lake. See that? And you're made a lot of water. It's kind of neat how that all came together. All right. So in the Celsius scale, 0 is where water freezes, And what temperature does the water boil on a Celsius scale? Everybody. It's easy, 100, isn't it? 100? It's even, they even took a power of 10, didn't they? 100 degrees between 0 and 100, isn't it? That's pretty neat. Okay, now, did we do body temperature last Friday? The whole world knows their body temperature in Celsius, and now you do too, don't you? So if you went to another country and they say, I don't know, I'm feeling very good, and they said, oh, your temperature is like 39, you said, yeah, I thought I had a fever. Because 37 is body temperature around the world, isn't it? Somewhere close to 37. And what about a comfortable room? If you go to Italy, you go to somewhere else. What's a comfortable room around the world? Aurora, what do you got? Give me a hit on that number. What should you be comfortable, a little bit more comfortable with the metric system? And somewhere around about 22, okay? Somewhere around 22 Celsius is a nice, comfortable room, right? Now, 72, I don't think it's going to get up to 72 today. So I had to guess it may only get to 20 Celsius today. All right, do you have any questions on that? Now, let's take a look at the equations again. You will have to memorize these equations, but it's not a big deal. It's not a big deal. Let's do the first one again. Since I live in the United States, they're probably going to give it to me in Fahrenheit, right? And what's the song say? If I want to go from Fahrenheit to Celsius, the first thing you do, subtract 32 5/9. Yeah, okay. Now, so we'll just try one today. I happen to know that dry ice is about minus 110 degrees Fahrenheit. Okay, so if you have your calculators, let's see if you can figure out what would that be in Celsius. What is minus 110 in Fahrenheit equal to in Celsius? Again, you should have this one memorized pretty soon. You have till Friday, but first thing to do is subtract 32 5/9. Yeah, that's pretty easy. You got it? What do you got? Oh, negative 110. Can you see the screen? I'm sorry. My fault. Dry ice is about minus 110 Fahrenheit. Well, thanks for asking. My head was right in the way, wasn't it? Now, find the person who sits closest to you and tell them what you got and see if you got the same one as they got. Okay, just kind of turn around and say, what'd you get? What'd you get? Say it again. I only had one. The other person came and picked his up. I had two. Do you normally not in math class? You guys use calculators? What you guys don't? Did you lose? All right, you just don't have it with you. Okay, if you want to go get it, we're going to use it a little bit. But all right, what did everybody get? But Daniel, what'd you get?
Negative 78.88.
That seems about right to me. Did everybody get that? Somewhere around about minus 79? Okay, so dry ice is pretty cold. All right, now I'll show you some little things that are a little bit higher level. If you don't mind, I just because you are in, maybe you don't want to take the honors math, that kind of forces you in here. I don't want to treat you like you couldn't be in the other class. I think you could. But I want to show you a couple things that are a little bit higher level things I hear. Do you notice that if you look at these two numbers here, this is both water boiling, right? And if you were to subtract these, you'd get 212 minus 100 is about 112. There's about 112 numbers between these two. Then you go down here to body temperature, 98, 37. That's not 100 and that's not 112. They're getting closer, aren't they? Look down here, 32 and 0. The two numbers are getting closer to each other. And look down here at absolute 0, minus 460, minus 273. Well, now they're kind of far apart. What does that mean? The two numbers are getting closer to each other. The Fahrenheit number and the Celsius number, they're getting closer. And at the end, they're far away again. You know what that means? There has to be a place where Fahrenheit and Celsius read the same number. Okay, let me see what I have in my wallet here. Does anybody know this by memory? Okay, I'll give you $1. First person to tell me what temperature does the Fahrenheit temperature scale read the same as Celsius? So just punch it in. Why don't you start at 0? 0 Fahrenheit. Try that. No, don't try it. It's on the paper. All right, minus 10. Go down to minus 10. Okay, it's getting closer. See, they're only 32 apart. Oh, there's only 18 apart. Go on down there. Go on down. Try it. Try minus 10. Try minus 80. What temperature would the Fahrenheit and Celsius thermometers read the same number? Say it out loud now when you get it. Say it out loud. You know you're getting close. If it's only like 3 apart from each other, you know you're getting close. First thing you do is subtract 32, 5 ninths. Yeah. First thing you do is subtract 32, 9 ninths. See? Keep doing it. Keep doing it. You got to be getting closer. Anybody? We know it's lower than 0 Fahrenheit. We know it's lower than that. Oh, you have to be getting close. What number? When you punch in a number for Fahrenheit, you'll come out the same one in Celsius. What is it? There you go. Negative 40. Everybody try negative 40. Very good. Good calculator use. Okay. Negative 40 degrees. Negative 40 degrees. That's a good Jeopardy question. How close are you? What were you down to?
Negative 6.
Negative 50?
Negative 6.
Okay. What were you down to? Okay. Was anybody getting close then? Okay. Good job. All right. So anyway, as far as this, let's look at the other one. And remember, I want to see if you can do this or not. First thing you do, subtract 32, 5 ninths equals degrees Celsius, right? Now, the other one is absolutely completely different. I want to see if you have it memorized without looking. So everything's different. So I start with degrees Celsius. Now I don't add or subtract first, I multiply first. But I don't use 5 ninths, I use what? 9/5. And then I don't subtract 32, I add 32. And if you do that, you get Fahrenheit. All right, everybody got that? Now those are the two that, if you memorize this one, you probably can memorize that one, because absolutely the reverse of that. But let me show you this here. Both of these temperature scales have a problem with them. It has to do with math. If you are going to use temperatures in some kind of a science equation, a math equation, let me ask you this question. I know you're going to think it's simple, but stay with me, okay? What's twice as hot as 20 degrees Celsius? What's twice as hot as 20 degrees Celsius? What do you think? Wouldn't most of you say 40? Okay. Even though that's not the answer, that's what sounds like it's the answer. Let's go again. Ready? Well, then what's twice as hot as 0 degrees Celsius? And you're thinking about your math class, and you say, I know what's twice as hot as 0. 0? What's twice as hot as negative 10 degrees Celsius? Negative 20. Negative 20 is twice as hot? It's colder. You see what happens? If you have a scale that has positive and negative numbers to it, it does not work well with mathematics. You get it? So, here's what happened. They said, we're going to take the Celsius scale, because we like it, Humans like there's only 100 degrees between these. And we're going to do it, and all we want to do is fix it. We want to fix the Celsius scale. We're going to call it the Kelvin scale. And all we want to do is, what is the coldest theoretical temperature that we think you can ever get anything? And it was minus 273 degrees. Now, they said, okay. I made a little pun there. They said, okay, that will be 0 Kelvin. And these actually aren't called degrees, they're called kelvins. So he said, ready? I'll take the lowest temperature that you theoretically think is possible, and I'll make that 0 in my new scale. That means we can never have negative kelvins. Never. And now watch how easy this is. What's twice as hot as 4 kelvins? 8 kelvins. Now, watch this right here. What's twice as hot as 0 Celsius? Slide over here. And by the way, if you take Celsius, you don't have to worry about the 0.15. If you take the Celsius and add 273, Celsius plus 273, you get Kelvin. And get that? Now watch. What is an ice cube in Kelvin? In Celsius, it's 0. But what is it in kelvins? What do? You take Celsius and add what? What do you add to Celsius to get Kelvin? 273. An ice cube is 0 Celsius. Add 273. What is it? 273. What about water boils at 100? What is that in Kelvin? We add 273. 373. Okay, so guess what? Let's try it. What's twice as hot as 0 degrees Celsius? Slide over here. Double that number. Use your calculator. Don't worry about the 0.15. Double the 273. What do you get? What's twice as hot as 0 Celsius? It's what's twice as hot as 273 Kelvin. What do you get? 5 something? Say it again.
546.
Oh, I lost a 5 what?
546.
32?
46.
46? I hate math. Okay, is that what you got? So what's twice as hot as 273 Kelvin? 546. But wait, what is that in Celsius? Look right here. Let me see how smart you are on a Monday morning, okay? A little algebra. If Celsius plus 273 is Kelvin, what is Kelvin minus 273? If I subtract 273 from both sides, what's Kelvin minus 273? Celsius. So here we go. What's twice as hot as 273 Kelvin? 546. Well, what is that in Celsius? Okay, let's see. Kelvin minus 273. Subtract 273, what do you get? You can't sit there and stare, okay? Don't just stare at me. Try it. If you take Kelvin and subtract 273, you get Celsius, don't you? What is 546 Kelvin in Celsius? You know. The reason you have the calculator is to help you think right now, all right? What do you have?
273.
And that's kind of neat. What's twice as hot as 0 degrees Celsius? 273 degrees Celsius. That's how you do that. Okay, I'm going to do one more thing that's just a little bit higher level, and then we'll get back into regular stuff. I want you to pretend that I own a company, and it's on the top of a mountain, and I named it the Acme Water Boiling Company. And the mountain's pretty high. And as a matter of fact, we're up pretty high elevation, and I have a pond down here at the bottom of the mountain, and the pond's always frozen. And by the way, this is an analogy. Does everybody know what that is? I don't really own this company, do I? But anyway, this mountain range, it's a whole mountain range. My employees are always getting mad because it's hard to walk up to work because I didn't have any stairs. They had to walk up, and sometimes it got slippery. So I called a company that made steps on this side of the mountain, and it happened to be called the Fahrenheit Step Making Company. Huh, what a coincidence. Anyway, I asked them to come out and make some steps, and they said, well, we will, but we have a real small job we're going to do, and then we'll come out to your place. And they came out to our place, and they said, well, how do you know how much to charge me? All of our steps are numbered. And the first step they used was number 32. And they kept putting steps and steps and steps and steps and steps. And when they got to the top, it ended up with step number 212. That's interesting. This is an analogy. You know, an analogy. Okay, so anyway, then how many steps are they going to charge me for? How many steps are they going to charge me for? Everybody in the room should be able to do this, okay? I don't care if you're in honors math or not. You can do this kind of math. How many steps will they charge me for? Started with step 32. It went to step 212. All right. Isabella, how many steps are they going to charge me for? Say it again. You're still figuring it out? Okay. You have it? No. Okay. I don't know. Let's see. Zach, you have a calculator? What do you got? What? Oh, okay. Layla, what do you have? Okay, let's think about this. What if you went to school with $32 and you came back with $212? If I were your parent, I would have to ask you, where did you get the... I know you had the 32. You went to school with 32. You came back with 212. Somehow you added how much money? 180. There we go. Isn't it funny where you say you can't do things mathematically and you start talking about money and all of a sudden you guys are great? You can do that in math a lot of times. Okay, so they're going to charge me for 180 steps. Now, on the other side of the mountain, there's a company who makes steps, but they're a different company. They're called the Celsius Step Company. And they said, well, you'll be the first job we get there. And they started with step 0 down here by the frozen water. It's an analogy. And then when they got done, they finished with step number 100. How many steps are they going to charge me for? Carl, what do you think? How many steps is this company going to charge me for? They started at step 0, they ended with step 100. That's right. Now here's my question to you. The reason I told you that story was, which one is a bigger jump? Going up 1 degree Fahrenheit or 1 degree Celsius? And don't guess. I want you to think about it before you say anything. Which one's a bigger jump? To go up 1 degree Fahrenheit, 1 degree Celsius, or are they the same? Isaac?
1 degree Celsius.
How do you know that?
There's like less numbers with Celsius.
Why did it only take 100 of their steps? It took 180 the other ones, didn't it? If it only took 100, each of your steps must be bigger, isn't it? And it is. If you go up 10 degrees Fahrenheit, that's not as big a jump as 10 degrees Celsius. Okay, another thing I want to show you, and then I'll move off of the higher level stuff, right? Here's what we do sometimes in school. I could even take some kids in college and ask them the same question. Tell me everything you know about the number 180 and 100. And they'll say, they're both even. You can divide them both by 2. Well, that's the same thing as being even, isn't it? This one's 80 more than that. I'll say, well, what else? That's about it. Now go to a 5th grader. Tell me everything you know about these 2 numbers. They're both even. And this one is 80 bigger than that. It's 80, yeah. Isn't that a shame? They go to school that many years, and that's the only thing they can tell me about those 2 numbers. And here's what happens. I'm gonna do something you don't like to do. But if you don't make yourself do it, you aren't going to get to that next level in thinking. You should always take numbers and make ratios out of them. Now, that's all I'm going to do is put one number over the other one, and I'm going to flip it upside down. And I want you to think about this. If I were your math teacher long ago, I would have taught you how to reduce the fraction. Reduce these fractions. See if you can reduce them. And I don't know how your teacher teaches that. I happen to know that both of those can be divided by 10. I might as well get rid of that right away. I just reduced it, didn't I? Now, can I divide something into 10 and 18? All right, what do you got? Madison, what do you got? What now? Okay. May, what do you think? What? You don't need a calculator. Can you reduce 10 18ths to something simpler? I know your math teachers ask you to do this, don't they? Don't they say simplifying? They love that word. Simple. What is it? What about the other one? The other one? Yes. Do you see that? Do you ever wonder why 5/9 and 9/5 were in the equation? Now you know. Okay? All right. Let's go over here, and then we'll finish this page and move on. The Kelvin scale is the SI unit for temperature. Now, if you're reading the book at all, you know that the metric system used to be called the metric system, but now it got modernized around 1960, and it became more than just a metric system, and it's now called the SI system. Now, what does the SI stand for? Does anybody remember that? Did I show you that in the book the other day? Your book calls it the International System of Measurement. That's because in English, we like to say things, the adjective before the noun. The red pencil. The red pencil. But if you take Spanish or French, they don't do that, do they? Anybody here Spanish? Anybody in second year Spanish? You are? Okay, how do you say the red pencil in Spanish?
I don't know pencil, but I know.
Do you know pencil?
We haven't learned that yet.
Okay. Do you know pencil?
Isn't it like lapis or something? I don't know.
How would you say the red pencil? I'm listening. What is it? Yeah, but you know in Spanish, they do not put the adjective before the word pencil. They would not say rojo and then pencil. They'd say the pencil red, wouldn't they? And I took French. What is it? Isabel knows? Well, tell me how to say the red pencil. Lapis rojo, right? And I took French, and when I learned it, I thought it was kind of funny that the French word for pencil was crayon. Okay, a crayon. Anyway, you say le crayon rouge, the pencil that's red. Well, so even though your book calls it the international system, what does everybody else in the world call it? It's the System International. And that's why, if you see it's in your book, they'll say the SI system. You get it? That's the International System of Measurement. The Kelvin scale is also known as the absolute scale because 0 on its scale is absolute 0, the theoretical coldest that anything can get. Also, but it's the same jump as a Kelvin is a Celsius. So if you go up 10 Celsius, you've gone up 10 Kelvins. It's the same size. There are no negative temperatures found in the Kelvin scale. That's why they made it, because you don't have negatives and positives in the same scale. Almost all chemistry and physics equations dealing with temperature require you to convert it into Kelvin. All right, the Fahrenheit scale was named for who? Take a guess. Take a wild guess. What?
Faraday.
No, that was close. Ooh, that was close. His name is Gabriel. You don't have to know his first name. Fahrenheit. His name was Fahrenheit. What? The Celsius scale was named for. What do you think? His name was Anders. You don't have to know his first name. Celsius. His last name was Celsius. The Kelvin scale was named for. Give me $1 back. Just kidding. John Thomson. Now, it just so happens, though, that John Thomson, he actually was given charge over this large amount of area in England that had the Kelvin River running through it. So he was known as Lord, not Lord Vader, that's Star Wars, Lord Kelvin. So anyway, John Thompson's name was also, he was also known as Lord Kelvin. Anyway, so they called it the Kelvin scale, named after him. Guess they could have called it the Thompson scale. There's only one temperature where Fahrenheit and Celsius reach the same number, and we already found that one, minus 40. How many temperatures give you the same number as Celsius and Kelvin? How many? 1, 2, 100? All of them? None of them? What do you think? Anybody take a chance? I don't have $1 for you, but what? What is it? Oh, that's for this one. But what about the Fahrenheit? What about Celsius and Kelvin? Any ideas? How about take a stab at it? Just take a stab at it. We gotta get going here.
7.
What? 7? Ooh, no. 6? No.
8.
No. 10? No.
98.
How much?
98.
No. You're getting cold.
15.
Your first
11.
11? Now you're getting cold from your first guess.
25.
Real cold. Huh? 4?
Four.
You're getting warmer.
3.
You're getting warmer.
2.
You're getting warmer.
1.
You're getting warmer.
0.
0. Now, how do I know that there are no temperatures in which Celsius and Kelvin are the same number? Look at it. Kelvin is always 273 higher than Kelvin. It always is. You get it? They will never read the same number. Kelvin's always 273 higher than Celsius. There we go. Okay, then this one you don't have to do. If you like mathematics, though, you can try to figure it out. There is a temperature where Fahrenheit and Kelvin do read the same number, but I'm not going to do that today. Which is the greatest actual temperature change? I got chopped off here. Is it 10 degrees Fahrenheit change, like it went from like 20 to 30, or is it 10 Celsius degrees, or is it a change of 10 Kelvin? If I saw if I had 3 thermometers and the Fahrenheit went up by 10, the Celsius went up by 10, the Kelvin went up by 10, which one of those represents the greatest actual temperature change? You're shaking your head. Which one? All right, you think it's Celsius? I will agree that the little story over here, I win. I know that I'm bigger than you. I know that 10 jumps on the Celsius is bigger than 10 Fahrenheit. I know that. How did you get this there? Here, Sierra, how'd you? And what? Okay, so now you think this is bigger than that.
Yeah.
Why?
There's no negative. So
Because what?
there's like no negative.
Now this is not the actual temperature. It's how many times. I had 2 thermometers. Okay, I have a Celsius thermometer. It went like from 20 to 30, and this one went from like 20 to 30.
Yeah.
So which one is the greater actual? I agree. This one's out. Now it's between these two. Let's take a vote. How many people say if your thermometer goes up by 10 on the Celsius scale, that's a higher jump than 10 Kelvin? Who thinks that Celsius wins? Oh, okay. Who says Kelvin wins? All right, who didn't vote? Why not? Okay, you didn't want to take a guess? Okay. All right, what's the answer? It's a trick question because it's the same. Remember, if you go up 10 in the Celsius, how much is that on the Kelvin? 10. Remember that? The Kelvin scale is the Celsius scale. It just doesn't have any negative numbers, does it? Okay, a little trick question there. All right. All right, we've done significant figures, and we did accuracy and precision, didn't we? That's what it says on my thing. All right, now we have one more thing to do. I want to show you in your book, let's see, here's, the last thing we'll do today is, a book here. Now, if you don't have your book with you, that's okay. You can just watch on the camera here. Oops. All right, here we go. Now, here is a word. I'll tell you what I did. I didn't have to give you this. I don't have to. If you don't want it, you can throw it away. This is what I was going to put on the camera today anyway. I said, well, you know what? No, it's not typed. But if you want a copy of this, you don't have to write so much. This is what I'm going to do here. So I'll give you one of these. This is just what I'm going to put on the camera. All right. We already practiced the top there. We already practiced some temperature conversions, so we don't have to do that. And then, so there are the last 2.5 pages in the book, in the chapter 2, talks about this thing called density. I talked to some other students, and they said that in middle school, at least once, you guys did something with density. Is that right? Is that right? I remember doing that. Okay, so that doesn't mean you understand it. It just means that you at least, it's not completely foreign to you, all right? So, what is density? And you probably remember in your middle school class that density is equal to mass divided by volume. So it's a calculation, and maybe you wrote it like this: D equals M over V. And if you want to get your driver's license, you have to go to the Department of Motor Vehicles. If you want to remember the order they go in. So what happens is you're going to have the mass, which is going to be probably in something like grams, and you're going to have a volume that could be in milliliters or cubic centimeters. And I'll tell you what makes that look weird. When you see something like that, you say, what is that? What do you mean the density is 3 grams per cubic centimeter? See, that's already kind of weird, isn't it? It has a mass unit and a volume unit, and that makes it look kind of weird, doesn't it? That's called density. Now, if I had to ask you, what is the theory behind the word density? I have 2 cubes here, and both of those cubes have the same volume. Volume means how much space you take up, and I can actually see volume. You see that? I can see they have the same volume, can I? Which one's heavier? You can't see that. I can put it on a balance. I can even do this. I got it. One of these is heavier, isn't it? But I can't see that. Density is whoever can pack the most amount of matter in the smallest amount of space is the most dense. I didn't do this, but God made these atoms differently. And he made them so that when you put them together, I can't compress them. I can't make them any smaller. This guy will have a density somewhere around 2.5 grams per cubic centimeter, and this is about 8. This guy packs almost 3 times as much matter in the same amount of space as this one. I'll pass this around. You can feel it. They both have the same volume, but they have different masses. If you put more mass in the same space, you're more dense. Here's one. Here's another one. These happen to have the same mass. These are all about somewhere around 70 grams. What does 70 grams of aluminum look like? That. What does 70 grams of lead look like? That. Why can't you put 70 grams of aluminum in this space? You can't. I didn't do it. But think about this. Which ones are more dense? They're both are 70 grams. So which one? This one or this one? This one. He puts 70 grams in a small space, doesn't he? And you had to put 70 grams in a big space. You're more spread out. You're more compact. You could say density is like, how compact is your matter? Now, when you pass these out, just be a little careful with them. But they all represent about the same mass, but they have different volumes, don't they? There you go. Now, I'll show you the next thing I'll show you. You're going to find out, if I don't get to it today, I definitely will do it the next day, Wednesday. When they were making the metric system, they wanted everything to be simple. And I thought they did a great job on that. So here's a box. Now, I'm going to turn this box upside down. Now, this box is part of the metric system. And I know it sounds strange because this doesn't happen in your system. But When they eventually had the meter stick, they said, this is good for measuring distances. We can even use powers of 10, and we can measure things like, here's a meter. Here is a tenth of a meter. Everybody use your hand like this. If you put your hand like that, that's a decimeter for most of you. Put your thumb together. A decimeter, and you should find a meter stick and find out what part of your hand is like a decimeter. Okay, that's a tenth of a meter. And then your little finger, you should find out what part of your little finger is a centimeter. And a centimeter is going to be about like this. So everybody should know what a centimeter is. And then the edge of a dime is a millimeter. So let's go backwards again. A millimeter, the thickness of a dime, millimeter, centimeter, decimeter, meter. Everybody got that? Now, what they did, which no one else had ever done, ever, they said, this is a neat stick to measure with. But you know what's even better? I'm going to build this from this. Now, they probably thought for a while that they could say, I'll make it this long, the box this long, I'll make it this wide, whoa, and this tall. Okay, number one, no one would ever use it, would they? It'd be too big of a box. You might say, well, then use a half of a meter stick. No, that's not powers of 10. If you're not going to use a whole meter to build a box, the next choice is 1/10 of a meter. And that's what they did. They made this box 1 decimeter long, 1/10 of a meter wide, and 1/10 of a meter high. They did it on purpose. If you have this stick, you can make this. Everybody got that? Now, what happened is then they found out that they decided that if you fill this with water, it's going to have a mass. And they said, what should we call that? They could have called it a gram, but that would have been a lot for a gram. And if you had a little bit of gold, you say, how much gold is that? 0.005 grams, and people don't like that. So they said, if you fill this box with water, it's going to have a mass of 1 kilogram. Now, a kilogram is about 2.2 pounds. And these are all connected. They did that on purpose. And I'll show you what they did here as far as density. Look right here. If you fill this with water, it has a mass of 1 kilogram. Now, a kilogram is the same as 1,000 grams, isn't it? And then what is the volume of this box? The volume of this box is 10 centimeters long and 10 centimeters wide and 10 high. What's the length times the width times the height? 10 times 10 times 10 is 1,000 centimeters times centimeters times centimeters. So now I have the mass. If I fill this with water, it's 1,000 grams of water. If I fill this with water, it's a liter, also known as 1,000 cubic centimeters. And on purpose, look what they did. On purpose, what's the density? It's mass divided by volume. What's 1,000 grams divided by 1,000 cubic centimeters? On purpose, they made the density of water what number? Okay, everybody look at me, okay? What's the density of water? 1. They did it 1 gram per cubic centimeter. They did it on purpose. So, for example, what I'm looking at here, this has a density of about 8. And by making the density of water 1, if I had a cube of water this big and had a cube of copper, if you have a density of 8, that means you're 8 times more dense than me. And what's the density of water? 1. Then that means I'll weigh 8 times more than you would. A cube of water this big and a cube of copper, this will weigh 8 times more because its density is 8. That's 8 times bigger than 1. Gold. Gold has a density, it's one of the super dense materials on the planet. It has a density of 19.3 grams per cubic centimeter. If I had one of these filled with water, it would have a mass of 1 kilogram. 1 liter of water would have a mass of 1 kilogram. But what if I had this much gold? I love you, but I'd probably stop teaching. Because I don't know if you know the price of gold. You know the price of gold? If I had this much gold, this is a lot of gold. As a matter of fact, it would not just be 1 kilogram, it'd be 19.3 times 1. It would be 19.3 kilograms of gold. If this is 1 kilogram, this right here, if it's filled with gold, it will weigh 19.3 of these. Sometimes you see on the movies where they're stealing gold bars. And then they throw it in the back of their truck. No. Imagine this thing right here weighing 19 of these. You think you could throw that 3 or 4 feet in their trunk? No. Matter of fact, by the time they put about 10 of those bars in a car, the springs would break and the car would go down to the ground. That's okay. It's Hollywood, isn't it? If they just take some iron and paint it gold, that's good enough for a movie, isn't it? Just tell the actors, pretend like it's really, really heavy, and they do. But it fools you all the time. They do it all the time. They have people in white lab coats, you know. They usually give them glasses, maybe a pocket protector, and that's good enough for you. That must be a scientist, right? You walk into the lab, and they always have test tubes. And guess what? That's in the test tubes is something that's red and blue and yellow and maybe green. Oh, that's a scientist. No. A box of food coloring comes in red, blue, yellow, and green. And that's why you see those. So it doesn't take a lot for some of you to say, that must be a scientist. Same thing with the movies. That must be gold, because it was kind of heavy. But if I told you this, if I fill this with water, it weighs this much. If I fill this with gold, it weighs 19.3 times that. That's a lot of these. So here's density. And the next thing I'll do, and then we'll stop today, is I want to show you something that you may or may not have done in middle school. I'm going to put some water in here, and I'm going to read it. This has to do with the next page in your book. They have a swimmer. I'll go ahead and show you the picture. They have a person at the top of the swimming pool. See that? Now, I just made this number up. I just wrote this in a book. I hereby declare there are 5,000 liters of water in that pool. I just made that number up, didn't I? Just made it up. Now, the person goes in the pool, and the water goes up. The water goes up to the line that says 5,300 liters. Where did the extra water come from? I'll show you how that works. Let me put some water, a little bit more water in here. I don't need a whole lot. Okay, so I'm going to read this. 43. Okay, so what I'm looking at right now is there are 43 milliliters of water in my graduated cylinder, okay? Now I'm going to do this right here. See this bar? I'm going to side in sideways so I don't crack it. Uh, 67. Now, the question is, do I really have 67 milliliters of water in here? How much water's in here? 67. No, that's not. I put this much water in there, 43. Why does it say 67? Because what used to be where that metal cylinder is? What used to be right there? Water. Where is it? It got displaced. It got pushed to the side, didn't it? And so it made it look like the water is more. We don't have more water. But look what I can do with this. This is kind of neat. Let's subtract those two numbers. I started at 43 milliliters of water. Now it says 67. How much did it go up by? 24 milliliters. What used to be here? 24 milliliters of water. What's the volume of this cylinder? What's the volume of that cylinder? Show me you can think, okay? What's the volume of this cylinder? What used to be right here? How much water used to be right there where that metal is? How much? 24 milliliters. What's the volume of that piece of metal? 24 milliliters. A milliliter, by the way, is the same as a cubic centimeter. And so you can actually find, look at the swimmer. What is the volume of that swimmer's body? Let's see, it started at 5,000. It went up to 5,300. I didn't put more water in there. The water went up to that, didn't it? What used to be where she's at right now? Water. Where is it? It got pushed aside, got displaced. And they do this sometimes with top athletes. They want to know what percent body fat they have. Well, how do you find the volume of a human? You do this, water displacement. And they can actually calculate the body fat index. And there are some athletes that are unbelievable in the lowest amount of fat they have in their body. You and I have quite a bit, especially me. Okay. I will not see you till Wednesday.